times R. So here it's written in terms of A, not in terms of R. So, okay, we knew that. All right. And so we did it. Okay, now I want to go and to write, to take the full equation and to write it with, and to linearize it, okay, to first order in the perturbed quantity. Now, in order to do that, we have to do be a bit careful. The equations that I'm using, so far, are the same equation that I use for, the James analysis. It's the same equation. I haven't changed anything. The only thing that is different is the background. With respect to which I'm studying or doing the analysis. Okay, so that the background is different. The background before was rho equals constant, v equals 0, and so on. But otherwise, these are the same equations. Okay, so I'm taking the equations that I wrote before lunchtime, and I'm linearizing them. Okay, and I have to remind you that we use the equation in terms of the variables x and t. And t is the same time, we're not going to change it, but x, just the physical coordinates. So the way that you are used to do physics. Okay, you measure length with a ruler, you get something, and that's the coordinate that I'm using. Okay, so with this kind of coordinates, the linearization of the equation is giving me the following thing. So it's d by dt of delta. Okay, now I'm careful. I'm writing it in terms of these coordinates. So I want to say explicitly what I mean when I write it, because I'm going to change the coordinates. I'm going to change from the physical coordinate to the co-moving one. Okay, so I want to keep track of what I'm doing. So it's like, when we learned for the first time in the university or before about partial derivatives. How do you do the partial derivative of something with respect to time, to t? You keep x constant and you differentiate with respect to t. Okay? So we have here now plus h x dot. Now it's the gradient with respect to x. Okay? Or the gradient times delta equals to minus the divergence with respect to x times u. Okay? So that's the continuity equation to first order expressed in terms of x and t. Let's go to the Euler equation. Euler equation is the one for the acceleration, the time derivative of the velocity. So we have here d by dt of u, and keeping it with x equals constant, plus h it's x dot the gradient with respect to x, or the derivative, it's gradient, okay, times u, plus h times u. H, I remind you, is always h of t, okay. Now this equals to, we don't have pressure, so it is minus gradient with respect to x of phi 1, okay? And phi 1, we have here Laplacian with respect to x of phi 1 equals to 4 pi g rho delta times delta. So again, I want to make it very clear, because here is kind of a touching point. So when I'm writing like this kind of operator, I mean it's d by dx squared plus d by dy squared etc. Okay, so the x, y, and v are the variable. Alright, so now I want to do the change of variable. Okay, so I'm going to change my variable from x, the physical length, to r, the common length. Okay, so I'm not going to change the notation. I mean, all the functions delta of x and t, I'm just using the same notation delta of r and t. Phi of x and t is like phi. But the only thing that I have to be very careful about is about the derivatives. There I have to be careful about changing the variables. So if I have here the gradient with respect to x, okay, let me write it like that. So it's dx1. I mean, it's partial derivative with respect to x1, and with respect to x2 and 3. Okay, so these are like the x, y, and z notation. It equals to 1 over a of the gradient with respect to r, right? Because x equals to AR. So it's easy to see. A bit more tricky is the time derivative. So the time derivative is you differentiate with respect to t and you keep x constant. Okay? Now if you do, but the transformation from x to r involves a time-dependent quantity. Okay? So the way to do it is this equals to d by dt, where you keep r constant, minus a dot over a times x dot by dot dx. This is an operator. Okay? Given the time, given everything, I leave it for you to prove it. Okay? It's kind of a tricky thing, but do it carefully, and you show that it's actually it's working. And actually, I see that x dot dx is like r dot the gradient with respect to r. You can also prove it for yourself. Okay. So after I'm using this kind of substitution, my equations 1 and 2 are now getting, I'm expressing them now in terms of, the reason that actually I'm leaving it like that is because I have here this term, and you see that this is nothing more than the Hoffman constant. So you see that actually this term here is like the one that I have here. Okay, so that's why I'm keeping it in this form that I wrote it for. Okay, so when I'm substituting this new definition, in particular, I'm doing the transformation correctly for the derivatives. The equation that I'm getting now to equation d by dt of delta with respect to r minus equals to minus 1 over a gradient with respect to r of, the divergence of u. And the second equation is d by dt of u, where I keep r constant, plus H Q equals to minus 1 over A gradient with respect to R of psi 1. So you see that actually the partial derivatives of d by dt, when you keep x constant, you get this d by dt when you keep r constant that you have here, minus h naught times x dot gradient. And so you have there it's with a minus, and here it's with a plus, so you get rid of this term altogether. Okay? So these are actually the two equations. That we are obtaining. From here on, it's very, very similar to what we did with the original, the stationary backward Gibbs analysis. So what we're going to do is I'm going to take the time derivative of equation 1 and subtract from it the minus 1 over A, the divergence of with respect to R, okay, of equation 2. Okay, and so instead of having like two first order equations, I'm going to end up with one second order equation. That's kind of the standard thing that one is doing all the time. Okay. Now, before proceeding, so that's what I'm going to do. Now, because that's what I'm going to do. Okay. Now, from now on, when I write d by dt, I mean actually d by dt will I keep r constant. Okay. And when I'm writing the gradient, I mean the gradient with respect to r. Or divergence of one of the equation. Okay, I don't want to keep on writing it because from now on I'm going to use only co-moving coordinates. All right, so we can forget about how we divide it, and we just remember that when we differentiate with respect to time, we keep it with r constant. The r dependent is constant, and the same the gradient is gradient with respect to r. Okay. So the equation that we get is following. D squared by dt squared delta plus 2 A dot over A, which I remind you is our constant, times first derivative d by dt delta equals to 4 pi g rho times delta. Looks familiar? Looks familiar? Where do you see it? Where do you see this equation?
Linear equation or equation?
Right, it's the same equation that we derived. Remember, we obtained this equation, okay, from the linear evolution of the density perturbation of the topic model. There, the derivation was strictly correct only for spherical perturbation. Right? And now we obtain the same equation in the more general case. I didn't assume any symmetry or anything. Right? For the most general perturbation that I can think of, all right? I'm getting this kind of an expression, this kind of an equation. So it's the same linear equation. Whatever we say about solutions and so on that we had for the top hat model, this solution also holds here. Okay, it's the same thing, it's the same equation. So essentially, we just we cover the same. So we just show that what we obtained there in the general, in the specific case of a surface symmetry, is actually it holds also for the most general case of what we're considering. Okay. Now, please see again that actually what we have here, delta in principle now is delta of R and T. But see that actually, so first of all, it's a linear equation by construction, right? We don't have on the coefficient, on the operators or coefficients that are multiplying the delta, we don't have any specific R dependence, okay? Because this term here depends only on time, okay? Because it's the mean density of the universe that is just changing at a to the minus 3. Here we have time derivative, and again, a function of time only. And here it's only, second time derivative. So again, we don't have any specific R dependence. So we can write the equation as some delta of R times d of A, d of time. Okay? And putting these answers, actually we see that actually the equation that we obtain are d double dot plus, let me write it like this, 2h d dot equals to 4 pi g rho d. And d is depends only on the time. Okay, so that's the equation. Now, I can repeat what I told you when we were dealing with the linear equation of the top hat of the dynamical evolution of the top hat model. That actually, but there was no need to separate it in delta of R and d of t because it was one single perturbation. We didn't consider a t. Okay? So essentially, what this equation, the ability to do this kind of separation of variables means one thing. That actually, suppose that we have some density, some density perturbation field and some very elevator, okay? And suppose that the density perturbation field looked like, now you're going to get me in terms of my ability to grow, okay? So, let's call it a cartoon. All right. So suppose that we had just, let me do my life easy. Suppose that we had a sine, the perturbation, the delta of R was a sine function, okay? Suppose that at some early time, it was something like that, all right? And suppose, so that's like, it's some A, I, okay? And suppose that I'm going now to a later time where d of A divided by d of AI is, let's say it's 2. Okay? So the only thing that is going to happen is that my perturbation, the amplitude of my perturbation is going to be doubled by a factor of 2. Okay? So it's going to be, so this is like my attempt, I meant to make it, this kind here like twice the amplitude here. So it's the same kind of field in terms of the R dependence. It's just the amplitude is changing, the whole amplitude. You can imagine that one is, don't imagine, just take it from here, the fact that it's changing like, the whole amplitude is changing without changing the spatial behavior. And now you see why it makes so much sense to use this kind of delta linear that I was talking about like the morning and yesterday. Because delta linear means, we don't care about the dependence here. The R dependence remains the same as long as it's in the linear regime. Okay, it's only the d is changing. And d is something, this growth factor, we can write it as a function of t or a function of a, then the growth factor is something that once we specify the cosmology, it's end of story. I mean, I can calculate this d of a, it's something that we talked about yesterday, and I just have to know the cosmology and calculate it, and I can scale it up and down as much as I want. It doesn't make any difference whatsoever. So why not to scale it in terms of quantities of today? That's the logic, that's the reason behind it. Okay, so we can write it in such a way, and let's look at the solution of this equation. Something interesting. Okay. All right, so we're here. Let's look at some solution of this linear growth function. Say in Spanish, número uno, like the first one, first case. All right. And you know what's the número uno. Answer the sequel. So, omega naught is 1. Rho equal to rho naught times a to the minus 3. We know that a goes like t to the 2 third, okay, or let me write it here. A is t over t naught to the power of 2 thirds, and we know that a dot is, or let me write it, a dot over a is 2 thirds 1 over t, and what else? 4 pi g rho bar equals to 2 thirds t to the minus 2. So I have here everything that I need. So this is stuff that you should know now by heart. Somebody wakes you in the middle of the night, you should be able to say it without any hesitation. Okay? So I'm substituting actually whatever I have to. What do I need? I need to put here the time dependence of h and the time dependence of 4 pi g rho bar. Right? So the equation now gets the form of d double dot plus 4 over 3 times d dot over t equal to 2 thirds d divided by t squared. All right? Very simple ordinary second order differential equation. And so what we are going to do, we're going to say let's try a solution of the form that d goes like 2 to the gamma. Okay? So when I'm doing this, what I'm getting actually is that the equation becomes, instead of a differential equation, it becomes an algebraic equation. So we have gamma times gamma minus 1 plus 4 third gamma equals to 2 thirds. And all of us know how to solve it, and we have two solutions. We have 2 thirds and minus 1. Okay, because it's a second order solution, right? So essentially what we have 2 solutions. So we can write it in the following way, delta of R. Now, we have 2 solutions, so in principle we can write it in the most general way of some, let me call it delta plus, the plus standing for the growing solution and minus for the decaying. So I have here like t to the 2/3 plus some delta minus of R, t to the minus 1. Okay, so in principle we have 2 solutions, one that is growing in time, the other one that is decaying in time. 2 comments about it. Let me write it as, just for the sake of making it similar to what we were writing before, with the Hoffman model. Okay, let me write it like that. Okay, so 2 comments. One is that if we wait enough time after Ti, actually, we are going to get rid of the decaying mode solution. Okay, then what we have is a delta of R in T, delta of R in T is going to be completely dominated by the growing solution. Okay, and we forget about the decaying solution. Or if you divide it T to divide Ti to the 2/3. The decaying solution just decays away. Okay, so that's nice. Okay, so if we have a choice of how to set up the initial condition, and we can tune it that we have like one component that is growing, the other one that is decaying, then after some time we don't see the decaying anymore. So that's comment number 1. The other comment is the note that what we are getting, that the growth of the perturbation is a power. It's not exponential like in the case of the stationary background. So essentially, when we consider the perturbation that we had in the Jigs analysis with the fixed background, so the background was there, was doing nothing, and when we did the analysis, we found that actually either the perturbation that were growing or decaying, they decay they grow or decay exponentially. So when you have something that is growing exponentially, you don't have to worry much about, the amplitude of the initial condition. You know that the exponential growth is so fast that, like, in no time, you're getting up the desired amplitude. And anyway, once you reach the end of, once you reach the nonlinear regime, okay, then the linear theory is useless, and you'll have to do something else. Now, in this case, we are getting here just a parallel. And parallel grows much more slowly than exponential growth. Okay? So in cosmology, the amplitude of the initial perturbations plays a very important role in describing or discriminating between different cosmological models. Okay? One of the needs, usually you hear arguments about dark matter. Why do we need dark matter? You go in the street and you meet somebody and you ask him, why do we need dark matter? He's saying, rotation curve of galaxy. Right? That's the standard thing. Or if somebody asks you, okay, why do we need dark matter? You start Zwicky and clusters and Vera Rubin with rotation curves of galaxies, right? And that's why we need dark matter. It's true, that's a good reason why we need dark matter. But there is something which I think is even more fundamental. And that is that when we look at the amplitude of the density of the fluctuations in the background radiation, okay, you see some emission, some amplitude for the initial perturbation. You can show that actually the amplitude that you have in the delta T over T, I don't remember it's a third or how it goes, but it's of the same order of magnitude like the delta rho over rho. It's some initial phase, okay? Now, if we were living in a baryon-dominated universe, then a universe with only baryons, stuff like us, no dark matter, then perturbation can start to grow only from about redshift, the Zi is about 1,000. And when you start with a growing perturbation from redshift of 1,000, okay, actually the linear, I mean, in ice and the theta, what we find, okay, if you write it further, what you get is this equal to delta, to this delta plus of R times A, right? Because A goes like T to the cells. So actually the amplitude is going like A, okay? So the most that you can get from linear theory, in terms of the growth of the structure, okay, is only a factor of 10 enhancement before you reach the nonlinear regime, okay? And when people started to look for fluctuation in the CMB for temperature anisotropies, at first they didn't find anything. Then we just had upper limits, and the upper limits were going down and down and down and down, okay? And at some stage, in the mid-80s, early 80s, the upper limits on the delta T over T were around 10 to the minus 4. So it was clear that if you have the initial perturbation have an amplitude of 10 to the minus 4, and you have only enough time to grow them by 10 to the 3, you are missing an order of magnitude in time in order to form structure. We just cannot form structure without it. So it turns out that if you have dark matter, you can grow structure from an earlier redshift, okay, larger than 10 to the 4, okay, close to 10 to the 5, okay. So from the theoretical point of view, the main motivation, or maybe the strongest motivation to have dark matter is that in order to satisfy the constraint that we have from observation, that this number is something, a factor of few or 1, 2 or something, 10 to the minus 5, okay, we need to be able to grow the structure earlier than what baryons are allowed. And so not being able to do it with baryons, people started to look for alternative, and that's the part of, I think it's a very, very strong motivation to have dark matter. So if people start to argue with you about, MOND, this and this, all sorts of things, their analysis, dynamics of on the scale of galaxies or clusters of galaxies, we have another very good reason why we need dark matter. In order to be able to make structure. Otherwise, we won't be able to make. Okay, so so we have this. What else? What other example we have? One more comment. If you look at the equations that we have, then actually, if we were not living in an expanding universe, suppose that the universe, for some reason, at one moment decides to, the universe says to himself, enough is enough, I'm fed up with expanding, let's rest a bit. So if the universe rests, h, the Hubble constant is 0, because a dot over a is 0, and then we don't have this term anymore. Without this term, actually, we are recovering back the solution for the non-expanding background, so the fixed background, and we are into exponential growth, okay? But the universe is expanding, and h is changing time, and it's not zero, and so on. And so, I mean, you can look at it, and for those of you who are familiar with the fluid equation or some other cases, I mean, actually this term acts as like friction. Okay, so we have a friction force here. Why? Because remember, I mean, these are kind of also kind of problems that we give students, you know, in first year in mechanics. So you have friction force that goes like, you know, either time dependent or constant times the velocity with a minus sign. So if I'm taking this term to the other side here, it appears with a minus, and it works like friction. So the expansion of the universe actually works like friction that prevents this d, the growth factor, to grow as fast as it wants. So the kind of solution that we find here actually are kind of a compromise between the fact that the gravity drives it towards exponential growth. The expansion of the universe is kind of slowing it down by a kind of a friction, and so rather than getting this exponential growth, we are getting this power. Let's go to the case of, and one more comment. Actually, so I wrote it here as d of t. Very easily, I can write it as d of a, right? You know it by now. In fact, I changed freely between time and extension time. All right. This d of a, which is essentially it's the solution of that equation, is the same d of a that we discussed yesterday. Remember we had a d of a there? It's the same d of a. So the d of a that I'm finding here, it's the same one, so it's the solution of this one, that I was mentioning yesterday. But yesterday, I just mentioned it without showing how it has been derived and so on. And here is the solution of the equation, this d of a needs to obey. The other thing, so the other problem that I'm going to find to solve for, we have here an open universe, and we are looking at this open universe in the limit of times going to infinity. Okay, so it becomes very empty. It becomes essentially an empty universe. Okay, for such a universe, I think that we have shown it. A goes like t, okay? And the density is negligible, zero, okay? So the solution that we have actually is d double dot plus 2 over t, okay? Because if a goes like t, then a dot over a is t. And now we have here 4 pi g rho delta, and actually the density is going to 0, and one can show, and I leave it to you to show, this one goes to 0. And the solution that you get for such equation, so the equation that we are going to solve is that one. Double dot, here I need d, okay? The d dot. Alright, so the solution that we are going to, the equation that we are going to solve is d double dot plus 2 over t times d dot equals to 0. And what we are going to get is the solution. So the solution that we are going to get is that d goes like gamma, and gamma, if you substitute here, it's a piece of cake, we find that it's either 0 or -1. Namely, once we are in the stage, if the universe was an open universe with only cold matter, once we're in the stage that that it behaves like an empty universe, actually the density perturbations don't go anymore. Because, I mean, the gamma that we have here for the going mode is 0, so there's no growth. Okay? So we call it, once we are in this state, then the perturbations get folded. Okay, they don't evolve anymore, while the decaying mode keep on decaying like t to the minus 1. Now, since actually Tuesday, the first day that we started our lecture, I told you all the time, pay attention to this factor of 3/5 that appeared whenever we had the perturbation. Remember, we had 3 over 5, 0 over 5 coming again and again and again. And I want to show you now what's the origin of this 3 over 5. Okay? So I want to be back to the Einstein de Sitter case. Okay? And I have here a delta t, which let's call it, so it's some initial profile. So actually I put in the profile with delta I, okay? And now I write it as like, I'm saying that I have 2 components, one for the growing mode and one for the decay mode, okay? So I have alpha to the power times t over ti to the power of 2/3 plus alpha to the minus 1 t over ti to the minus 1. Okay? So you can imagine that this is a profile. Delta I is of R, if you wish. Doesn't matter. Okay, so I'm just splitting the amplitude that I have in between the going mode and the decay mode, nothing more than that. Okay, so essentially what do I have here? I have that at some, the initial time delta ti, it equals to delta I. Okay, now, I want to fix the alpha that I have here such that at time ti, the perturbation that I have is only in the density and not in the velocity. Okay? Namely, I want to fix the alpha such that u at time ti equals to 0. That's my choice. I have the choice for playing between the alpha. Okay, I can choose any alpha that I want to have. Okay, because it's solving a second order differential equation. You have 2 parameters, 2 integration constants to play with, and you can play with the 2 in order to satisfy, let's say, the initial conditions or any other conditions that you want to have. All right. So. What we have here is, I'm going back to the continuity equation that I already erased, but if you remember, we had the equation that d by dt of delta, okay, equals to minus dv divided by a. Now I'm saying that at ti, I'm asking that u at ti equals to 0. All right. So what I have is that d by dt of delta at ti equals to 0. Okay? So let me take it. Let me differentiate this thing by time, evaluate it at t equals to ti, and equating it to 0. Okay? It means that I have here an equation for alpha. Let me do it. So what I'm getting is So I leave it for you to do the exercise, okay? So differentiate delta of t, substitute at time equal to t equal to ti, and equate it to 0. What you are getting, in order to fulfill this condition that alpha equals to 3/5. Same 3/5 that came up, popping up all the time since Tuesday. And what did we get here? We started by requiring that the initial time we only make perturbation on the density and not on the velocity. Does it ring a bell for you? Does it ring a bell for you, this condition, that we just perturb the density and we don't perturb the velocity? That's exactly what we did with the top edge. Remember, I stressed it again and again. Again and again, yeah, only twice, but this one again and again. Once when we did it only for the EDS, and then when we did it for the general case. I stressed it that I'm picking up a particular choice of the initial condition. This particular choice is such that I'm perturbing just the density, and I'm not perturbing the velocity. And what's the consequence of it? That the ratio or the distribution of the power between the growing mode and the decaying mode is such, that's true for dinosaur theta, that it's the growing mode is getting 3/5 of the power, and the decaying mode is getting the 2/5. All right? Now, when I'm waiting long enough, this one doesn't exist anymore. Okay? So it means that actually, let me write it here. So after enough time, after Ti, what I'm getting is that the delta of R and T goes like equal to delta of R. It goes like 3/5 of delta I, let me call it like that. Okay, T over Ti to the 2/3 power. So that's exactly the 3/5. So the thing is that in terms of the actual delta I that we had to put here, or to put here, or to put what we did for the Hoffman model, actually after enough time, we are left only with 3/5 of the original power. That's the reason for this 3/5 that came all the time. Now, now, this is a rigorous solution for an Einstein de Sitter case, but we can show that for any kind of cosmology, let's say that we take flat cosmology with a cosmological constant. If we start at VI, which is early enough, like a redshift of 1,000, then at the beginning, it behaves like an Einstein de Sitter universe. So this kind of division of power of 3/5 to the growing mode and 2/5 to the decaying mode, actually, we find it also from other cosmologies. All right? If we do it properly, this kind of okay. Okay, but it's a rigorous solution that we find for this. What else we want to do? Honey.
Yes.
I haven't done velocity and the Lorentz approximation. I can rush and do it in like 10 minutes, but I'm not sure it's really worth it. Or we can just write it kind of nicely and we'll scan it, or take it, never mind, and then we can distribute it to the participant.
Which one do you prefer? 10 minutes?
So 10 minutes, 15 minutes, or you want to get it in writing and then we can discuss it next week. Up to you. You want what?
15 minutes.
15 minutes. You want to want 15 minutes. Okay. I want 15 minutes. All right. Okay. So there are two more topics that I want to discuss. Yes, one more kind of small comment about what we got before. So we started to writing in terms of this D of A. So, I mean, often we write that the perturbation is going like dr of t, going like something times dA. And we say that we are already in the going mode domain. So never mind what was the original Zi that we start. Let's say the Zi, like what I suggested you to do with the top-end model was 1 plus Zi was 1,000. And then once we go to a shift of 100 or 10 or something like that, we are deep into the interlinear regime, but getting rid of the decay mode, and we just consider that. So when we write dA, we mean the dA of the decay mode. So dA, actually, we mean, I'm sorry, the going mode. We mean that it's the dA of the going mode. Okay? So if I write G, the gravitational field, okay, I can write it as G. Now I write it in the most general way, times A times D of T or D of A, doesn't matter. Okay, so it's the going mode thing. And what we have here is just the usual expression that we all learned in the first year of the university mechanics, that we have delta R prime, R minus R, so that, never mind, and here, never mind, R minus R prime, okay? So this is the gravitational acceleration without all the units and all of that. Okay, so this is a dimensionless quantity. Okay? If you substitute it, this is yeah. This is a page. Let me keep it. I'll go back to it. I put the pages in the wrong order. Okay, so yeah, I want to rewrite the equation that we have for the perturbation now as an equation for the velocity. Okay? Because before I had two equations, I differentiate each one of them separately, and I got instead of two equations, only one equation for the but of the second order. I want to go back and to do it for the velocity. Okay, so velocity is remember we call it h naught x plus u. Okay, so it is okay, we wrote it like that. So I want to redefine the u and to write instead of u, to write it as a times the peculiar velocity. All right. So this is the perturbation, and instead of writing it like that, we just write it as a times vt. And the only reason why I want to write it like this is that then I'm getting that the velocity. I can write it like a to the h naught times r plus v of t, and So if I'm going back to the equation d by dt of u plus h times u equals to minus 1 over a convergence with respect to r phi 1, then actually when I write it d by dt of a dt, it equals to a d by dt of vp plus a dot a times vp, all of it, plus a h vp, okay, which is actually it's the same term that I have here. All right. So now the equations that I'm getting is going back to the two equations. D by dt of delta equals to minus the divergence of v of p. Namely, I got rid of this 1 over a thing that I had here, and d by dt of vp plus twice h vp equals to minus 1 over a times g, okay, and minus the divergence of g equal to 4 pi g over a times delta. Okay, so okay, so what I have here is so if I'm taking the time derivative of this last equation that I got here, so I'm taking here, so I have a delta here. Let's say that I take this factor 4 pi over times g rho bar times a. I divide it by the left hand side, and so I'm writing here d by dt of divergence of g divided by 4 pi g rho bar a, okay, equals to the divergence of v. Okay, so what I have here, I can take actually, all the terms that I have here, all the concepts that I have here, depend only on time. Okay, so what I can do actually, I take the divergence and just put it in front of this expression. Okay, and so what I'm getting at the end is that, actually I didn't have to take it up. So what I'm getting is that Vp, okay, actually equal to, it equals to d by dt of g divided by 4 pi g rho over times a plus some kind of a function, some general function of some r of t, where the only limitation that I have is that the divergence of this function is 0. Essentially what you see actually is that I took the divergence out and I said, what's the divergence? The divergence is actually with a differential operator. So I integrated with respect to this differential operator, and the solution that I'm getting is what I'm having here, plus a function whose divergence is 0. Okay, so I can have here something like the curl of it can be non-zero, but its divergence is zero. Okay, so altogether, just one second. Okay. Okay. Just got confused by the. Okay. All right, let me just state the following. One can show that the part that we have here corresponds, so the velocity perturbation, the v of p, the peculiar velocity, has now two components. One component whose divergence is not zero, that's the component here, and another component is divergent is zero, okay? And what I'll be showing later, and it can be shown, is that this component actually belongs to the decaying mode. It's in the decaying mode. Okay, so if we are considering perturbation only in the going mode, then we can assume that after some time, what we have that the v of p actually equals to this thing, the v of t of the term here with the g, plus a decaying mode. So if we just wait long enough, we get rid of this mode and we don't have to consider it anymore. So from now on, what I want to do is I want just to concentrate on this thing that I have here. And I already wrote here that I can write g in this way that I wrote here, okay? So if I write g in this way, what I have is that v of p is just this dimensionless gravitational field, g of r, this is the thing, g of r, divided by 4 pi, and now I have the time derivative. Instead of having here the partial derivative, now it becomes the full time derivative with d. Okay? So with a bit of algebra, I'm not going to do it here because we are really late. The final solution that we are getting is the following. We are getting that the peculiar velocity equals to g. Now I'm writing the full thing with the g field. Okay, over 4 pi g rho bar times a. Okay, now it's 1 over d d by dt. Okay, I have now, because I have this expression for d. I have this growth function d, so I'm getting it back here. So that's what I'm getting at the end. And we can write it all like v of p, vp equals to h divided by 4 pi g rho bar times a times d over let me write it. If you write it like this, it's a over d times d dot over a dot. All of it is multiplied by g. Okay? So realize that actually this term here can be expressed in terms of omega, and then we are getting the final result that v of p equals to 2/3 some function of omega, and if we have also a cosmology constant, it's like omega naught, okay, divided by h omega a, no, it's just omega here, times g, where this function here, this function of omega and the cosmological constant is nothing more than this logarithmic derivative of d divided by a times d dot divided by a dot, which is d. Okay, I'll leave it like that. All right. What we are getting here is that actually in the linear regime, the peculiar velocity goes like the gravitational acceleration. In the linear regime, these ones are basically, essentially, it's like the same perturbation up to some constants that depends on the cosmology only. Okay, so if you know g, you know v. If you know v, you know g. Up to the constant that depends on the cosmology. And now for this function, you can find in the literature all kind of approximation for this function, and so if you're using it to calculate it directly, it doesn't matter. In the case of lambda being 0, that is f of omega naught goes roughly like omega to the power of 0.6. That's a very useful approximation that people are using. Okay. Now, it can be shown, and I'm not going to do it really for the lack of time, that if you consider a velocity perturbation, remember, we say that the velocity field actually it contains two components. One that goes like g, and it's like the gravitational potential. It's a gravitational potential. So this part actually corresponds to a potential flow. Okay, because v goes like g, and g is a gradient of a scalar potential. It means that actually v constitutes a potential flow. Okay. On the other hand, if you are considering the other part, then you can show that the other part actually is a rotational flow. Okay, it derives from a vector potential, and it is completely within the decay mode. Maybe even if you start with some early component that has a vorticity, this component will decay very, very quickly. Okay, and it decays essentially like 1 over a. Okay, like one of the scale factors, so we can neglect it. So this concludes. I'll leave the end of it short. Yeah, it's too much. So I have like one small piece that I haven't completed. It's important, but somehow we'll give it next week, either by writing or I'll take maybe half an hour from Stefan or something like that. And that's it. It was a long way. So we finish here. Questions? Anything?